That is a coaxial cable extent which we are taking it and
This is the our antenna. So this is the software part, this is the patch, and this is the ground. So
Okay.
I want to means from patch I connected, this portion I cut, some
Ground portion only you need
substrate
to
also
cut
and
now.
then ground also.
if you want to make it actually what it is like, we had connected as a via here.
Yeah, that's all.
Okay, some kind of via. If you want to if you want to make it as a whole and then you want to insert it, that is also fine. You need not to do it with the computational software. If you place a cylinder in between, instead it won't be kind of a dielectric material in this particular cylindrical part. You need not to. I got your
Because there
question.
is a gap, is the air is there, so air has also the
If
dielectric
you want
constant,
to-
so it has to affect the.
Mostly how it will be is like we will be just connecting SMA connectors. I got your point. Like when you are in a practical case, when you are drilling it, it won't be exactly 0.1 mm.
Yeah,
There
yeah.
might be some kind of gaps will be there.
Yeah.
If you want to consider that you have
That's right.
yeah, you can do that also. That's not it. The only aim is like it has to touch the patch.
Like
Yeah.
this is for testing purpose only now, sir. Like for commercial applications and all, we don't go for this SMA connector.
Yeah. It will be.
we are
we'll be
using
going
that
for-
electrical ports or
But
dielectric.
for measurement we have to
Measurements,
this thing.
uh,
We will be like only the thing is like whatever the soldering is just happening in practical case. It is the point of contact.
Yeah, that's
Like my ground should be with the contact of my ground, the outer conductor. In SMA connectors, it is nothing but other than interconductor, whatever the
like
body
it will
which is
check
there.
the body also.
We that is wholly grounded only. Like in SMA connector, if you see, it will be kind of an
4-pin.
it will be inner conductor, and here again it will be a kind of an cable. Where the inner conductor only is the part which has to be touched with my patch here. Okay, this overall ground, whatever it is there, it will be connected with the ground. Like if you solder this part also with my ground plane of the patch or the ground plane of that particular antenna which I am making, it will be connected. So the whole body, it is ground plane. Only my inner conductor will be touching my patch here. So once you had made this, then as I said, I will be just attaching my excitations geometry at the bottom of the ground plane itself. Okay. So for that again draw. Go to circle. Draw it. You can make it as 3, 0, and the radius will be 0.2, which is the etched out radius. Click on apply and OK here. Okay, so this is the first thing which we had made, and the next step is on other than excitation geometry, everything has been assigned. You can check it out here. Just right click on circle 2, go to assign excitation, then ports. Actually in your version you will be getting lumped port option. Here if I am going with model analysis, I would have gone with the model lumped port. Here I have terminal lumped port, which is the terminal solution. In solution type I had selected terminal, so I'll go for.
So in case of electrical, if in case we don't use that SMA connector and we go for some electrical connection, electrical type,
Yeah.
discrete type, so what port should we use?
We have discrete port also.
Discrete port is available.
Circuit ports.
Okay.
That's
So in that case we are using circuit.
Circuit ports will be there. So other than that, in this also based on applications, we have different types of ports. Okay, plain incident wave for RFID examples if you are going. So in that particular case, or in like plane wave excitation, if you want to see, like in unit cell, we'll be making an lattice pair boundary condition or master slave, and we'll be analyzing. Instead of that, if you want to analyze a meta surface kind of a thing, just how a plane wave is interacting, how my incident wave is getting reflected back, or for RCS analysis, radar cross section analysis, all these stuffs we can go with this.
So we are giving here like waveguide port only.
I will be going with there is nothing much with waveguide and lumped port. Both are similar kind of port analysis. In wave ports, we need to give the PEC backing should be there. Okay. If it is lumped port, we no need to go for that. terminal lumped port, whichever is the ground plane, choose it as reference and click OK here. So now we had created all kind of things, only the boundary condition is remaining here. So to go for boundary conditions, you can right click on the layout, go for create open region option here. Once you create open region, if you give the operating frequency here, based on that your airbox will be created here.
It automatically created. Huh?
Yeah, it will automatically create. We need not to create geometry for it. For an example, it is around 27 to 28 gigahertz. So once I click on it, the airbox will be created. Okay. So this is the overall procedure, and then the next step is, this is like kind of an geometry creation, like the 2D or 3D structure creation, and based on that what kind of material we are going to give it to it, and those kind of geometrical analysis we did. Now the next step is we need to go for
size of that airbox?
lambda by 4 from this particular
All
edge.
directions.
In all directions.
From edges or centers?
From edge. From this particular edge, it will be lambda by 4.
Substrate.
Yeah. Substrate, or if you are extending on top, like for an example, if you are giving some thickness to this copper also, from that copper face, it will be lambda by 4.
So radiation also you can use, no? Radiation box.
Yeah, you can create a different radiation box. Like
So we need to assign it as a radiating surface, radiating thing, or
didn't get which
so
this
we
box.
design the box and we need to make it as a radiation or something like that, or
No, automatically if you go for open region,
Oh.
instead of radiation box, radiation boundary condition only, just open region boundary condition will be appearing here. Okay, if you want to make a lambda by 4 of box, and you can right click, again you can go for assign boundary, and
तुम्हारे हाथ
you
से
can
कट
see
ही होता है
radiation.
दुनिया का चीज़ है.
Okay, okay.
either you can go for in this way also.
So if we want to increase or decrease that lambda distance,
That
we,
you
we can do it like manually, right?
Yeah, you can here, you can go here. Once you have created this open region,
Okay, okay, okay.
you can go here, double click on this create region. Manually you can see in positive X how much it has to be increased. That also could be done. So once you have created this particular boundary condition, the next step is we need to go for analysis. So here we will be setting up what is the frequency range it will be, and what kind of convergence rate we are going to give, and what is the number of passes here. So right click on analysis, go to add solution setup, go for advanced here. Auto it will take from 1 gigahertz to 10 gigahertz of range, wherever it recognizes it. If you are just like that you are creating your model, you can go for auto. In our case we will go for advanced. So here we have 3 different solution frequency, which is single, multi-band and broadband. So here in this case it is only single band which we are looking for. So for that the frequency range I am giving it as 27 gigahertz, and number of passes just I will make it as 10, maximum number of passes to be 10, and maximum del S value to be 0.02. In this itself I will show how based on field concentration how adaptive mesh works. So in this particular case everything is getting reflected back. My field concentration will not be on the patch here. It will be very minimal if I see the field concentration. So how many number of passes for this it takes, and how many number of passes when I exactly match that, how many number of passes or mesh structures, how it confines, that we'll just compare that to get a clear idea what adaptive meshing is about.
So if in case we are going for multi-band antennas, we
Huh.
have to give like multi-frequencies, right? Like
Yeah, we'll be giving
previously it is not
multi-frequencies.
available, I guess.
Maximum del we'll be giving here for each and every frequencies. Sweep actually it will come next to 100.
Okay.
So once
There
you
is any calculations there for maximum del?
meshing, based on meshing structures only we have to reconfigure it. It's not about calculations. Based on this maximum del S, you can visualize the meshing, how confined or how the smaller the meshing structure is
Okay, you asked the
building
window,
on
then
the
I saw.
structure. If it is too much large, if it is not concentrating any particular part, then you have to refine your mesh again. You have to decrease this particular maximum delta S, and then again you have to simulate and see.
So it should be minimum as possible.
Minimum as possible.
You can go for 3, 4, 1, 0, 0, 3, 0, 4.
To take more time to run,
No,
that's
no, no.
the
If
issue.
increasing it is taking less time only. If it is decreasing,
it is-
it is taking.
But the accuracy again is like missing, no? If you
At
increase-
last, the time of 3 years of span we are spending only for accuracy.
yeah, it is.
It's not about getting faster.
So once you get some fair result, you will increase the missing, you'll increase the
Yeah.
delta
We
value.
just you magnitude like
I think
what is
that
the
I have
difference?
to record the
Like,
sounds
you
also.
will be getting, in some cases also you might be refining too much that your magnitude whatever you are getting it will be very
Completely
much
collapsed.
Yeah. But when you go for measured results, it will be a minimal value. You will be getting in simulation, it will be around 30 to 40 dB, minus 30. So here, let's say maximum number of passes 10 and del S 0. Once I click on enter, the frequency sweep option will be coming here.
Here
Here
again.
you have. I would suggest always go for interpolating.
So what's
Once-
the difference between this discrete interpolator and
Fast, what it will take is how the frequency sweep will be happening is like. For example, in this case, how much it is? 13.5 gigahertz. 13.5 to 40.5. Fast, what it will do is, it will take these 2 points, it will take intermediate, like between these two
Okay,
frequencies, intermediate point it will take, it will solve, then again this kind of
Average,
approximation average, and again the second point. So how it will be is like the first simulation, how it will be like between these two frequencies it will calculate. Again these two point will be there. The step size whatever we are giving till that particular point or else 4.1, I usually go for step size where I will define what should be the minimum step size of frequency. So that number, based on that number till that particular point it will go. The same way interpolating will be, but fast is not that much accurate. You can go for that to just for to when you are going for optimization, all these kind. You can go for fast and interpolating. Discrete, what it will do is, it will take 13 point. Basically, it will start from the higher frequency. It will take 40.5. Then let's suppose it is the step size is 0.25. The next point it will take is 40.25. Again, from this it will take the next
40.
step. It won't be like an approximation from each and every step. How it is I can say it is not kind of an approximation. It is a kind of an value next to that. It will calculate and how the field is responding. That it will give in this particular sweep option here. So always go for interpolating in the initial stage. When you are going for fabrication or giving the model to the vendor who is going to fabricate it or the PCB designer, go for discrete, take those values or take that particular graph when you are publishing for papers. Don't go for interpolating.
so discrete is much accurate than
It will be much accurate and it will take too much of time to simulate.
Okay.
The last option, once you feel like in interpolating you have got a better result, the result will again it will be refined much better in discrete. So in this we will go for linear step, and I know it is around 27 to 25 to 28 gigahertz. So I'll just reduce the step size to reduce the simulation time. So I'll make it as 20 to 32 gigahertz, and then click OK.
So what about the far field and all? Like we need to define any particular setting for far field.
Here, once we go for open region, we need not to set far field radiation. We need not to set anything.
Okay.
If you are not using open region, in this particular radiation, you have to go for far field setting. Infinite sphere, you have to set it out here.
Okay.
If you are going for open region, automatically it will be set out here. So once we are done with this, just we'll simulate and see what it is. For simulations, go for simulation tab. First, validate it. Any kind of 3D model error if you are having, that you can check it out, and at last you can go for analyze all here.
So what's the like?
Sorry, it's scanning something else. I have not selected this model.
Save the survey, right?
No, it's actually the project name. It is. Seems okay. It is under that project. So just to view how the processing is taking, you can go to right click on this setup. You can go to profile option here. It will let you know what how much time it is taking for frequency sweep. Now it got completed. From starting, what is the step frequency, how it is taking. All these data while running simulation you can like for smaller simulation it is not much needed. When you are going for large simulations where core is much needed, so at that time you can do that. And convergence, you can see in third number of pass itself, my simulation got completed. And here the convergence rate we had attained. In initial case, the number of elements or tetrahedral structures was created. It was 13,396. Then again it increased the number of structures based on field. Then it saw the convergence rate, which is 0.03, which is greater than my value of the target value. And then the third iteration it has got it, and the simulation got stopped. But the number of passes which I gave, it was 10.
So within 3 it is completed.
Within 3 itself it got completed. Why? Because my target value of maximum 10 is
achieved
achieved.
already.
Okay. So this is one case. Now if I go and see reflection coefficient, anyhow I got no, it will be mostly fully it will be reflected back because of impedance mismatch. So once I go to result, right click, go for terminal solution, rectangular plot, then just click on new report. So whatever I am sending here, it is nearby 0. Whatever I am sending through the port, it is everything is getting reflected back only. Nothing is transmitted to the radiator. Okay. So now let's suppose I know the position here. Just
So this is S11 only, no?
yeah, it is S1. Yes. This is S11. That is the cylinder one structure which we had kept. This is nothing but the reflection coefficient. Let's suppose I know the position here, which is around 0.6 mm from the center. That will be the matching position. Okay. So let's suppose I'll change this. I'll introduce a parameter here to change the overall system. Like
So
position
this is the
X.
position of the feed, right?
Yeah. So this is position X is nothing but the change of position from center to the feed location, exact feed location where impedance is going to be perfectly matched. So it is asking for that. I will give it as 0.6 mm. The same way I have in this particular excitation system, I have three components to be coupled together for an excitation system. One is my inner conductor, then the dielectric region, and my excitation
So we
geometry.
need to change everything.
Everything I have to change it over here. If I had used some variables, I could have just changed directly.
Okay.
So the first inner cylinder I had changed it. Then I will go for the lumped port here, which is my port geometry, 3 mm plus position X. The same way, the dielectric region where I had subtracted it out, which is circle 1. Here also I include that, which is 3 mm plus position X. Click on apply and OK. You can see here the overall system once you try to zoom in. The overall system based on the input here, like let's suppose I am making it as 1 mm. So all the system should be moving together. So let's suppose it is 0.6 mm as I said. We'll just run the simulation and we'll see how many number of passes it had to. Okay. So initial case I'll make it as 0 itself. And let us first plot the mesh here, how it looks like we'll see.
So here itself we can do the parameter analysis and we can find out the
Yeah.
feed position exactly.
So this is, I suppose this is my rectangle one. Just we'll plot mesh here. In field overlay, whatever the fields you are making out, just we need to run the simulation. As I included new parameter, the old solution it is not taking there.
So it will delete the old one and
You can see here how the meshing for each and every number of pass it's increasing. So this is how the mesh is looking like here. So wherever my field is trying to concentrate more, like here it is trying to interact. Okay, so in that particular area it is trying to confine here. But let's suppose I'll change the position here, which is from 0 to 0.6 mm. So let us run this. In earlier case we got it at in third number of pass we had got the computation to be done. You can see the number of meshing or the structures is increased when compared to the earlier one. And once in profile, if you see, it would have went beyond 3 number of passes. You can see at 10th number of pass only we are attaining that. Okay, and the number of tetrahedral structures which we had used is 11,000. So this will define my accuracy there. So why it is because once my reflection coefficient is distributing, then only the fields will be coming out. So based on fields only my convergence will be happening there. If you make a mistake in feeding technique itself, then whatever the result you are getting, that won't be an accurate one. So this was just to demonstrate how the number of passes impact and how the convergence happens based on the field distribution. So what is the lunch time actually? Not aware.
No, we don't have any particular.
Now it's already, sir. It's running.
Okay, lunch is from?
Probably
text, right?
So 2:32.
Okay, we'll come again at 1:30 then.